Hi, welcome back. All right, let's go ahead and move on to quiz number 5. All right, cool. You guys should be seeing my screen right now. Okay, so let's go back to question, or not go back. Let's go to question number 1. All right. So right here, consider the following reaction. Now it gives us a reaction, also gives us a delta H or enthalpy, right? And if we notice that negative sign, it's exothermic. And if it's exothermic, then heat is a product. We'll keep that in mind for later. Now, let's go ahead and tackle, all right. State the direction of any shift in equilibrium, left or right, as a result of each of the following changes and give your reason. All right, so right here, this first one's really easy. Oops. So for adding HF, HF is a product, all right? So if we add product, it has to shift to the reactant because there's excess product and it just messes up the entire equilibrium. So it has to make up for it by increasing the reactant in order to shift back down. All right, so adding more HF or a product will shift left. More product, shift toward reactants. All right, increasing the temperature. All right, if we increase the temperature, oh, oops. Give me 1 second. Sorry about that. Okay. Increasing the temperature. So if we increase the temperature, and remember it's exothermic, so temperature or heat is a product, increasing the temperature would increase product. And just like our first situation, it would shift left. Temperature is a product. And increase in product causes a increase in reactant and obviously lowering of your product in order to reach that equilibrium again. Now, if we decrease the volume of the container, this goes back to our gas laws. All right, so if we decrease volume, that means we increase pressure. And let's go ahead and count our gaseous moles here. All right, so this is a gas. We have 2 moles of gas, 2 moles of gas, M is moles. We have 1 mole of gas, 6 moles of gas, 1 mole of gas. So we have 4 moles of gas versus 8 moles of gas. Let me double check. Yeah. Okay. So if we increase our pressure, right? So let's say this is our normal pressure at equilibrium. If we increase our pressure towards a positive pressure, okay, our system wants to basically alleviate that high external pressure by bringing it back down. An order way to bring it back down is to decrease the amount of gaseous moles so that there's less particles that are zipping around, hitting the surface of whatever container you have it in. So if you're trying to bring it back down, you're trying to shift it to the left. Because the left has your 4 moles, which is less than 8. And if it has less moles, then it should decrease that pressure and basically alleviate that change you had. Now, right here, let's remove Cl2. Cl2 is a product. And if we remove, let me box these. Don't forget to box your answers on the quizzes. It makes it a lot easier. It would shift right. For the same, or the contrary reason for the first part, all right? If we remove a product, then there's too many reactants, and according to our equilibrium constant, it must shift and make up for that. So it reaches that equilibrium constant again. So it'll make up for that loss product by just creating more of it. And if it's creating more product, then it's shifting to the right. All right, less product, shift towards product, or shift towards, yeah. All right, let's go back down here. Now, under what conditions of pressure and temperature should the following reaction be carried out in order to make the maximum amount of products? All right, so we're given this reaction right here. And again, we see our delta H is negative, so it's endothermic. So heat must be a product. Okay, well, temperature is easy. Because temperature, if it's a product and we want to make more product, we have to do we have to use low temperature, because if we use a low temperature, there's a lack of product, and thus the reaction wants to come to equilibrium by, excuse me, I'm at a loss for words. It's been a long day. The reaction wants to make up for it just by creating more product, which is your heat. Now pressure is a little bit of a weirder approach. So for pressure, let's count our gas moles again. So right here we have 6 moles of gas. Right here we have 4 moles of gas. So if we're trying to get products which is a lower amount of gas, we want high temperature, or not high temperature, high pressure, my bad. For the same reason of part 3 of 1, right? If we have a high pressure, then the reaction wants to make up for it by decreasing the amount of moles to lower that net kinetic energy, just to make up for that increase in external pressure, right? Because if our pressure increases, positive pressure, it wants to bring it back down. By bringing it back down, you're taking to the products, which is less moles. Right. Now, the solution has a pOH of 4.68. Calculate our concentration of OH, our pH, and our concentration of H3O+. This is really easy. Well, first off, we can actually already solve for pH. So pH is just 14 minus pOH. That's one way to solve for it. So let's do 14 minus 4.68. All right. We have pH, excuse me, pH of 9.32. All right. Now going up back to the top. So part A and part B. So for solving the concentration of OH, well, that's directly correlated with our pOH. So we just do 10 to the negative 4.68. That gives us our concentration of OH, not H3O+, not the hydronium ions. So if we just do that, then 10 to that will be, numbers that are there, 2.1 times 10 to the negative 5 molarity. All right. For H3O+, there are multiple ways of attacking this. So we could do 1 times 10 to the negative 14 divided by whatever concentration of OH we have. Personally, it's a little bit complicated, a lot more scientific notation that you deal with on the test and possibly mess up on. So what we could do is do the same thing we did for A, but with the pH we solved for. We can just do 10 to the negative 9.32. All right, and that would just give us 4.8 times 10 to the negative 10 molarity of H3O+. And to double check, you're welcome to multiply this by that, and it should be 1 times 10 to the negative 14. All right. I'm going to pause the recording real quick. All right, let's continue. Sure. All right. So going back up to here where we started. All right. Identify the acid bases and their respective conjugate pairs. All right. Well, I like to start just like leftmost, like the way they write it out, usually the easiest way. So HF, that should be pretty easy to identify as your acid, because HF is pretty protic. It's a halogen and a hydrogen are pretty much acid, so because it's deprotonated. And by process of elimination, this is going to be our base. And from our labeling, we can just do the opposite. All right. So our acid, when it's deprotonated, will become your conjugate base. And this is because, all right, in the reverse reaction, F minus, your anion, will be the one that's protonated and thus act as the proton acceptor. And the opposite reason for the base, right? So when the base is protonated, this will be our conjugate acid, because that bicarbonate, those bicarbonate ions will basically deprotonate and protonate HF, and thus the definition of our Bronsted-Lowry acid. So that was pretty easy. So what is the pOH of a 9.6 times 10 to the negative 3 molarity of HCl? Is the solution neutral, acidic, or basic? Well, we can already see, all right, HCl, that is a relatively kind of a big concentration acid-wise, and HCl is an acid, so I'm going to guess it's acidic. Let's go ahead and try to solve it, all right? So the pOH, well, we can solve by, or if we're given HCl, we can find the pH and then subtract 14. I think that's the easiest way we can approach this. So if, and we know, first off, HCl is monoprotic. It only protonates one hydrogen. And be careful, because sulfuric acid is diprotic. It's a polyprotic ion. It'll protonate twice, or can. So if we were to draw our ICL, just to ensure that we have the right concentration of H3O plus. So if we have HCl, H2O, we have H3O plus, and our conjugate base, or our anion, Cl minus. So if we have 9.6 times 10 to the negative 3, that liquids don't count at all, 0, 0. And we know that HCl is a strong acid, so it'll completely dissociate. Minus 9.6 times 10 to the negative 3 plus 9.6 times 10 to the negative 3 plus 9.6 times 10 to the negative 3. Well, that's just going to be 0. But this is going to be 9.6 times 10 to the negative 3. And that's what we're looking for, actually, H3O plus. So let's go and plug it in. Negative log of 9.6 times 10 to the negative 3. Let me find those numbers. There it is. Our pH is going to be 2.02. And you can't stop there, because remember, if this is our H3O plus, when we do the negative log of that concentration, it's going to be pH, because it's going to be the concentration of protons, not OHs, right? That's where a lot of people messed up on the quiz when I was grading them. You guys just circled the 2.02. You have to take it a little bit further. 14 minus 2.02, that's just going to be 11.98 equals pOH. That's going to be especially important. You don't want to make a dumb mistake like that on the test. Please make sure you read. If you have time, I would highly suggest you just go back, read the directions, like on top of your map, but read the directions, just make sure you did it correctly, because you'd be surprised. All right, now let's get the conjugate base for this acid, right? Now, this acid right here, we have C5H5NH plus. Well, it's kind of like the giveaway, NH plus, that anion is connected to that nitrogen, right? And that hydrogen is not affiliated with those hydrogens, and that's a singular hydrogen. So that's the one that's probably going to be, protonated. So C5H5N, that's going to be our conjugate base. And there is no minus sign, because remember, if you're removing a proton, right, you're moving a positive charge, and there's only one positive charge right here. Okay, so it's just gonna be like that. Pretty sure. Let me double check. Yeah. Okay, now let's do the opposite. The conjugate acid for HSO3 minus, and you see there's a negative charge. It's going to be a it's an anion. It's going to be a base. So if we were to add an H over here, we can add H right there. So H2SO3. And remember, you're adding a positive charge. -1, that's the charge right there. -1 plus, well, +1 is just going to be 0. There's going to be another no net charge. And yeah, that's kind of it. And don't mistake that. Note, remember sulfuric acid is SO4, is SO3. So if you do any calculations with that, make sure you don't like fully dissociate it. Now for this bonus question right here, which of the solutions is the most acidic? So by definition, most acidic would have the lowest pH or the highest pOH. All right, so the easiest way is either normalize all these and make all of these into pHs, or normalize all to make them all pOHs. For this question, I think I'm just going to keep it as pH. So pH is given to us 6.2. Now our pH equals just 14 minus pOH. Whoops. And thus our pH, that's just 12, because 14 minus 2 is 12. Now for this one, pH, this is H3O plus, so we will give us pH, negative log of 1.42 times 10 to the negative 10. Our pH is now, let me find those numbers, to be 9.85. All right, now let's go back to our definition. Lowest pH is going to be the most acidic, and that's solution 1 right here. That's it. Right. That concludes our quiz overlooks. If you still have questions, do email me. All right, you guys have access to my emails. Last minute questions. Good luck studying. And again, please reach out, ask questions, because you guys have a test coming up. This is one that you don't really want to mess up on. All right, good luck, guys.